Welcome back. In this video we are going to begin our exploration of radioactivity. But before we begin, we must further delve into the nucleus and some of the fascinating peculiarities of it. So let's start off with a quote by Walt Whitman. He says, "I believe a leaf of grass is no less than the journey work of the stars." So even though he's not a physicist, his statement is profound. When he wrote that line, he did not even have the slightest notions of how stars behaved. But eventually, once we learned about the stars, we do indeed see how a simple blade of grass exists because of them. So, Rutherford's experiment was critical to understanding the atom. He said that 99% of all mass is made up of protons in the nucleus of the atom. However, he forgot one fairly important particle, the neutron. It wasn't until later, when more experiments were concluded, that we understood that the nucleus now contains protons and neutrons. So here's some key terminology that we need to know. First are nucleon. So what are nucleons? Nucleons are either a proton or a neutron. So our next definition is the atomic number, or Z. Atomic number is the amount of protons in a nucleus. Next definition is going to be the neutron number, which is N, and the neutron number tells us the amount of neutrons in a nucleus. Our last definition here that we're going to have to look at is our atomic mass, which is A. And our atomic mass is the number of neutrons plus the number of protons in a nucleus. So that's going to be Z plus N is our atomic mass. So this is often written in a shorter way, where we have here this X, which is going to represent my element. So it's going to be either He for helium, maybe Au for gold, and something like that. Then we're going to have here, A is always going to be my atomic mass, is always going to be on top, and my atomic number, which is the amount of protons, is always going to be subscript. So superscript will always be my atomic mass, and subscript is going to be my atomic number. Now, if we look there aren't protons, but we know how to find, there aren't any neutrons, but we know how to find the neutrons by going my atomic mass subtract the amount of protons will give me my amount of neutrons. So let's try this example here. It says, how many protons, electrons, and neutrons are in an atom of gold? Well, we know my atomic mass is equal to my amount of protons plus the amount of neutrons. So in other words, my neutrons is equal to my atomic mass minus the amount of protons. In this case, I'm going to end up getting 197 nucleons, and we're going to subtract the amount of protons, which is 79. I subtract those, I'm going to end up getting 118 neutrons. So altogether now, we have 118 neutrons, I have 79 protons, and I have 79 electrons. So since this is an atom, my electrons must equal the amount of protons, so we have a neutral charge, and atoms tend to have neutral charges. In my next question, we want to know, how does the nuclei of carbon-12, 13, and 14 differ? Well, if I look at this, for each of these, my atomic number, which is the proton, stays the same. It's always 6. But something that does change is my atomic mass. Now, if my atomic number is staying the same, my atomic mass is changing, that means we're changing the amount of neutrons in each nuclei. So we're having more nucleons, but the protons aren't changing, so that means we're getting more neutrons. So these three types of carbon are called isotopes. They're called isotopes because they have the same amount of protons, but each one of them has a different amount of neutrons. Now, many atoms will have 2 or more isotopes, which means, once again, they have the same amount of protons, but differing amount of neutrons. So now pause the video, and here are 2 questions for you to try by yourself. This should only take a couple minutes, and here are the solutions to those questions. So now that we know about these nucleons and how they make up the nucleus, we might be questioning, well, what does these nucleons weigh? Now, before we even get into that, we have to think about it here. These are super small. Like kilograms, although you may see it on some of your diploma questions, are great for measuring apples and oranges, the human body, stuff like that. But we're talking about protons and neutrons here. These nucleons are super, super tiny. And yet they are the mass of the atom. So instead of using kilograms, we started using something called atomic mass units, where one atomic mass unit is equal to 1.66 times 10 to the negative 27 kilograms. Now, one atomic mass unit is equal to also 1/12 of a carbon atom. So carbon was the first one where we used to get these atomic mass units. And what they did was they said, well, we know there are 6 protons, 6 neutrons, and a carbon atom, in carbon-12. So what they did was they just divided it by 12, and that's your atomic mass unit. But then they did measurements later on, and they found out, well, protons and neutrons do actually have different masses. So if we look here at this table, we have the mass of a proton and the mass of a neutron in atomic mass units. And for doing calculations in physics, it is very crucial that you know both the proton and neutron, their atomic mass units, to 6 decimal places. And we're going to see why here coming up soon. So this may have worked for carbon, but here's something very interesting. And even if you notice, and we add these up, well, we said there's 12 altogether nucleons in carbon. We have 6 protons and 6 neutrons. And if we times this number by 6 and add it to 6 neutrons, well, we're going to get something bigger than 12, aren't we? Well, why? So interestingly, if we take any element and add up the masses of all the nucleons, the mass will be greater than the actual mass of the element. So what's happening here? This is absolutely confusing. How could we have a mass difference? How could we have a defect of mass when we put these nucleons together? So I want you to think about that here, and we're going to come back to this as to why that's happening. Now, let's first look at the forces of the nucleus. Apart from hydrogen, all nucleuses are made up of more than one proton and a number of neutrons. And we know that like charges repel. So what keeps these nucleons from flying apart? Well, first we said maybe gravity, but really it can't be gravity. Gravity is far too weak. There must be some other forces holding these particles together. And physicists call this the strong nuclear force. So the strong nuclear force is the force that binds together protons and neutrons. So that binding force must be responsible for this mass defect. Because if we think about it, mass cannot be created nor destroyed. In this case, it is just transferred into energy. So this is what is the nuclear force. So gravity is too weak to hold the nucleus together. This force is like an electrostatic force, but only works really, really close together, neutrons and protons. So binding energy. So the binding energy of a nucleus is the energy required to separate its protons. So let's think about that. We have a loss of mass there, and that was the energy taken to combine these elements together. Now to pull them apart, we're going to have to input that same amount of mass that was used to bind it. And that's going to give me my nucleons to be separated, or allow me to separate these nucleons. So in other words, the binding energy is equal to the energy of our nucleons minus the energy of the nucleus, where the energy of the nucleons is the sum of all the nucleons, and the energy of the nucleus is the sum of energy of the nucleus. So how do we calculate this? Well, remember, mass times the speed of light is energy. So really, we could also say this is also our mass defect. Remember the difference of the mass of nucleons to the mass of the nucleus. So then because of Einstein, and as energy is equal to the mass of something times the speed of light squared, we could always find out what is the energy here instead of using our mass. So remember, one atomic mass unit, and if we multiply that and convert it to kilograms, is going to be equal to, when we multiply by the speed of light squared, 931 mega electron volts, or 1.49 times 10 to the negative 10 joules. This is very important to maybe memorize, so you don't always have to use Einstein's formula to calculate this. And if you memorize that, Einstein really made this section of work pretty easy. All we have to do is find the differences of masses to calculate stuff. So our mass defect is essentially my binding energy once we convert it to energy using Einstein's equation, or multiplying my atomic masses by this many, 931.5 mega electron volts. So mass defect is the difference between the sum of masses of the separate nucleons and the mass of the nucleus. So here in this example, we have hydrogen. And first we take the mass of the proton, and we're going to plus it, or add the mass of the neutron, and then we're going to subtract the mass of the atom of hydrogen. So we add these, and notice we need 6 different decimal places, and we're going to keep on adding these, and then we're going to subtract the mass of the atom of hydrogen, which will be normally given to you, and that's going to end up giving you your mass defect, which is very important, because from there then we could find the binding energy, or the energy needed to pull these neutrons and protons apart. So binding energy is equal to mass defects times the speed of light squared. So mass defect and binding energy work very much hand in hand. So in example 2, we want to find the mass defect in kilograms and the binding energy for a carbon-12 nucleus. So let's look at what's given here first. We know the amount of protons is 6, and the amount of neutrons plus protons is 12, because that's my atomic mass. And in this case, we're looking at carbon, so 12.000 is my atomic mass units, since we use carbon to find atomic mass. Next, we want to find what do we need to know. We're trying to find my mass defect, and we want that in kilograms, and our binding energy, which is going to be in joules or mega electron volts. That is going to be up to you. So the first thing I must do is find the amount of neutrons, which is pretty simple. All we do is we're just going to look at my atomic mass, and we subtract my atomic number from it, and that's going to give me my amount of neutrons. Then we have to find our mass defect. Almost every time before we do our binding energy, we need to find our mass defect. So in this case here, we're just going to take our amount of protons multiplied by the atomic mass of protons plus the amount of neutrons, and we're going to multiply it by the atomic mass of neutrons. Now altogether, that's going to give me 6 multiplied by 1.007825, and we're going to say plus 6 multiplied by 1.008665, and then we're going to minus the mass of an atom for carbon is just 12.000000. And this is going to end up giving me a total of 0.0, and that is atomic mass units. We're just going to put a U there. So we want to convert this into kilograms. So remember, we said each atomic mass unit is equal to that many kilograms. So I'm going to multiply this number by that many kilograms. So I'm going to go 0.09840, and I'm going to multiply that by 1.660539 times 10 to the negative 27 kilograms, which will end up giving me a total of, and this is per 1 unit, which is going to end up, those will cancel off, which will end up giving me a total of 1.6429 times 10 to to the negative 28 kilograms. Now I want to convert this into my binding energy. So all I have to do then is I'm just going to go, we know energy is equal to my mass defect times my speed of light squared. So in this case, we already have this in kilograms, which is nice because we have to use the kilogram version to find my binding energy. So I'm going 1.6429 times my speed of light squared. And that's going to end up giving me a total of 1.4776 times 10 to the negative 11 joules. Or, if I want, I could put this in mega electron volts, which I just divide that by 1.6 times 10 to the negative 19, and then put it in mega volts, so then whatever times 10 to the 6. So in this question, as you can see, everything is a little bit different. In this case, we're looking in kilograms for our masses of the proton, neutron, and the atom of helium. So here we're going to have to find the mass defect and the binding energy. And this one here might be a little bit easier as it's a little bit less steps. So let's start off here with A. So we want to find my mass defect. So first of all, I have to figure out how many neutrons and how many protons there are. So if my atomic mass is equal to 4, that means I have 4 nucleons. And my atomic number is equal to 2, that means I have 2 protons. Now I subtract those, that's going to give me 2 neutrons. Okay, so now we know how many neutrons there are, we could find my mass defect. So my mass defect is going to be equal to the number of protons, or my atomic number. So we want the mass of my amount of protons, and we want to add it to the mass of my amount of neutrons, and then we're going to subtract the mass of helium, of the helium atom. So altogether I'm going to get 2, because there's 2 protons multiplied by 1.67, and then we're going to add 2 multiplied by 1.6749 times 10 to the negative 27 kilograms. And then we must subtract my mass of the helium atom, which is 6.6443 times 10 to the negative 27 kilograms. Now, altogether, that's going to end up giving me 5.07 times 10 to the negative 29 kilograms. So we found now my mass defect for A. Now, let's look at B. We want to find what is the binding energy. So my binding energy is equal to my mass defect multiplied by the speed of light squared. So I'm going to take my answer from A, and I'm going to multiply that by speed of light squared, which will end up giving me 4.56 times 10 to the negative 12 joules. And remember, if I want to change this to mega electron volts, all I'm going to do is I'm going to divide this by 1.6 times 10 to the negative 19, and that's going to give me joules per electron volts, and then I just got to convert it to mega, which is times 10 to the 6. And that's how I'll get my mega electron volts. So the last part of this video that we need to know before we get into radiation and decay is that you could compare the stability of different nuclei by dividing the binding energy of the nucleus by the number of nucleons it contains. So binding energy divided by my atomic mass, or the amount of nucleons, tells me how stable the nucleus is. So the greater the binding energy per nucleon, the more stable the nucleus is. And that becomes important later on.